permanganate in basic solution. Okay? Now, most of us, before we started talking about redox, would look at this reaction and say, Miss Herbank, nothing's going to happen, right? Because isn't potassium chloride KCl, and isn't potassium permanganate KMnO4? And we are very, very programmed when we see a reaction like this to think of what type of reaction?
Single replacement. Double replacement.
Double replacement. And in double replacement, don't these just switch places and you're like, Miss Herbie, you get the exact same thing. So therefore no reaction. This is not double replacement at all. This is redox where there's all new rules. Okay? So that's what we're going to learn about. Notice also that this is in basic solution. So I'm going to teach you how to balance in basic. Now, I differ from the way that the book tells you. Okay? I think my way is easier. You are welcome to use the book way. I don't care. Whatever's easier for you, you follow. But what I do is I follow the exact same steps, the first 8 steps for balancing an acid, I follow. And then at the very end, I add a couple of steps to switch the acid to the base. Okay? So that's how we're going to do it. Michaela. Is Michaela gone? No. Okay. All right. All right. So the very first thing I'm going to do is I'm going to recognize that these are going to be in solution. And so what's going to happen to a potassium salt in solution? They're going to break up?
Yeah.
Yeah. So this is going to be K plus and Cl minus. What about KMnO4? Is it going to break up? Yes.
Yeah.
We don't know anything about permanganate, but we know about alkali metal ions, right? Potassium always breaks up. Okay. And now, do you remember on page 74, there was a list of stuff that got oxidized and reduced? This will be new to Frank and Ariana because you guys were gone yesterday. Okay? But turn to page 74, and we're going to use that chart. Okay? So we're going to look for things. We're going to go on a redox hunt. Okay? All right. But first, well, first of all, which thing here seems like the strangest, weirdest thing? MnO4. And MnO4 is actually something that is commonly oxidized or reduced. And whenever I see MnO4, one of my redox antennae go up. Whoop, there it is, okay? All right, see that antenna? Okay, so I want you guys to look and look at what's staring you in the face at the top of your chart. What do you see? Page 74. Does everybody see MnO4? Yes. Now, do you see it twice?
Yes.
Yes. Which one are we going to choose for this problem? The one that says neutral or basic, okay? So, if we had to write a product, what does the chart tell us MnO4 in basic will do? Okay? Everybody should be looking right here in basic, and it goes over here, and it forms MnO2. So we're going to write that down. I know it seems like we're just making up stuff, but we're using the chart that people that have been doing redox a long time have formed. Now, according to the chart, what does MnO4 do? Is it being oxidized or reduced? It's being reduced. Mitch, show Ariana and Frank how to change their book. Remember how we changed oxidizing agents and we said that's being reduced? Okay, make sure you show them that. Okay, so this is being reduced. Now we got to decide between these two. But I'm noticing that the way that describes elements is often very generic. Okay? So, guys, tell me, K plus, what family is K in? It's in the 1A, and what name do we give that? Alkali metal. So this might be called an alkali metal ion. Okay? What family is chlorine It is a non-metal, but yes, it's group 7A, and it is called the halogens. Okay? That's a name that a lot of people forget, but when you have like a halogen lamp, something like that, that it has one of those elements. So these are halogens, and let me ask you this. When we talk about the ion of fluorine, chlorine, bromine, how do we name it? How do we name fluorine's ion? Fluoride and chloride and bromide. So these are often referred to as the halide ions. Okay? So now let's go on a hunt. Look on your chart on page 74 and see if you see alkali metal ions or halide ions. Which one of those do you see? Halide. And guess what, guys? Is it on the bottom?
Yes.
Yeah. If permanganate was already being reduced, don't we have to have something being oxidized? And that's in the bottom list. Okay, so does everybody see the halide ions? Okay, that's on the reactant side. Look and see what product it forms.
Free halogen.
Free halogen. What does that mean again?
By itself.
So it'll just be Cl.
By itself as an element. So I'm going to write Cl. But is there anything wrong with just writing Cl?
The diatomic.
It's diatomic. So when it says free, it means in its most stable elemental state. So if things are diatomic, write them diatomic. There's only 7, right? Everything else we just keep by itself. All right. So clearly, what is not involved in this reaction? The K plus. And let's think back to when we did net ionic equations. What always was a spectator? The 1A metals. K plus. So we're actually going to erase these. Not involved. Not involved. Okay? Okay. Now, if you look at the homework I gave you last night and that I'm going to give you tonight, isn't this kind of the format that they start with? They don't start with all of this. They start with the net ionic equation without the hydrogen in the water. Okay, without the H plus in the water. So this is where we're going to start this problem. Okay? All right. Now, we're going to do the quick way again. We're going to break them into 2 half reactions. Okay? Let's do it quick at first and then go back. So, give me two chemicals that'll be in the first half reaction. I don't care which one we write first.
Cl.
Okay? Cl. And then, Sean, what should I put over here?
Cl2.
Cl2. Good. Everybody agree? Great. And how about the next one? MnO4 minus and MnO2. Good. Now, if we had to label them oxidation and reduction, which one would be quicker to tell? The first one. What's the oxidation state here? -1. How about here? 0. Is it going up or down? Up. Is going up oxidation or reduction? Oxidation. So if this is the oxidation half reaction, the other is reduction. Does everybody understand how we did that so quick? Okay? Now let's go back and practice oxidation numbers just a bit. This we already figured out. This one, what do we assign to oxygen? -2. And if there are 4 of them, that would be -8. Okay? This whole ion is equal to -1. So what minus 8 equals -1? 7. So this is a +7. Okay? And then over here, oxygen is -2. 2 of them makes it -4. Does this have a charge? No, there's no charge written. So this is going to equal 0. So what minus 4 equals 0? 4. Okay. So were we right to say that manganese was reduced? Yes. +7 down to +4. Okay? Is that cool? All right. Now, I want to say one more thing about oxidation numbers. Okay? If you're talking about an actual ion, then the oxidation number is just the charge of the electron. I'm sorry, of the ion, because the ion has, in this case, gained an electron. Okay? But a lot of people were asking me, how how is oxygen -2? And how is something like chlorine 0? Okay, well, let's take a look at this. Do y'all have some kind of recollection in Chem 1 of when we talked about covalent bonds and that sometimes the sharing of electrons was uneven?
Yes.
Okay. And a lot of times we called oxygen a bully. Okay? And if you look on the periodic table, isn't oxygen over to the right?
Yes.
Okay? The fancy word we used is we said oxygen was more electronegative than hydrogen, which meant oxygen pulled the electrons in the bond more toward itself. Does that drawing look at all familiar when you drew arrows toward the bully? Yes, no? Maybe this. When you said this was partially negative and these were partially positive?
Yeah.
There's polar.
Yes, this is what we mean by polar. This is a polar molecule. Some of you might recollect on the first test, remember that I said, oh, you've got silver ions and you've got nitrate ions, and you guys had to tell me how the water lined up. And remember here, it was the oxygen side that lined up, and you guys said positives and negatives attract.
Yeah.
And over here, didn't the positives get close to the nitrate? Do y'all remember that? Okay, so this whole positive and negative thing is not because they're actual ions. It's that the electrons in this bond, let's call the electrons toys, okay? So oxygen and hydrogen are playing together, and they're playing with their favorite toys, electrons. But oxygen is a bit of a bully, okay? So whenever oxygen's mom is not looking, oxygen goes like this to hydrogen. Okay, mine, right? Okay, so oxygen is playing with the electrons more than the hydrogen, okay? It can't totally take them away because mom is saying, no, you have to be in a covalent bond, okay? You have to share. But it's a very uneven bond. Does that make sense? So because oxygen is pulling on one electron, 2 electrons, that is why we assign oxygen a -2 for its oxidation state. If we ever had to assign hydrogen an oxidation state, guess what we would assign it? Not a -1, but a +1 because it's having to do without its electron because of the bully. Okay? Let me ask you
Is
this.
that why it's always blue or
Yes?
Is that
Okay.
why hydrogen's all by itself because it doesn't like oxygen? See, look.
Yeah, that's why. Because it's no, not right. Okay, and then here, look at this. What did we assign as an oxidation state for chlorine? 0. Tell me about these guys playing together. Are they sharing their electron toys? Well, yes, because they're both the same bully or they're both the same weak, however you want to say it. There is no difference. So, since the electrons aren't spending more time with one than the other, then they have a 0 charge. That's why elements are 0. Does that make sense? Pretty cool. Okay, good. All right, so tuck that into your hat. All right. Now, let's go back to balancing. Okay, so really, we've used the oxidation numbers just to make sure that we've identified our half reactions, okay? So let's go back and follow the steps. And I'm going to start going a little bit faster so the bell doesn't catch us like it normally does, okay? All right, step 4 says balance everything except oxygen and hydrogen. So up here, what do I need to do? I need 2 chlorines. Good. Okay? And now, since there's no oxygen or hydrogen, this is kind of done for a little while until we get to step 6. Down here, are the manganeses fine? Yes, they are. Okay? But here I have 4 oxygens and only 2. So Brenna, what am I going to add?
you would add 2 oxygens.
Okay.
Yeah.
How do what your highlight says, balance oxygen by adding what?
H2O.
H2O. So I'm going to add waters, okay? And guys, stay with your list for a while until you're good, okay? So I'm going to add waters, but I have to add 2 of them. So now 2 and 2 is 4 oxygens, and I've got 4 oxygens here, right? Okay? So now I'm going to Maruna, I'm going to balance my hydrogens. How many do I have over here? 4. So what does your book say to add when we're balancing hydrogen? H pluses. So which side am I going to add them to? This one. Good. And how many am I going to add? 4. Okay? So now we've got manganese, oxygen, and hydrogen balanced. So all the atoms are balanced so far. We're about to tackle the charge. Yes, Star.
Where does the hydrogen come from? Where does it get?
Okay, you know how we say things are in acidic solution or basic solution?
Oh,
Okay? And let me just remind you guys real quick, because we're going to come back to it, Star. It's a great question. Remember water? Couldn't you kind of think of water as H plus and OH minus together? Okay? Oh, crash. Okay? It's all right. Okay? This is the acid ion. This is the base ion. Okay? So it's all gonna happen. So that's what happens in there. Oh man, let's stick these on. Okay. All right. Let's first look at the charge though. Okay? What is the charge of these two -1 ions? -2. What is the charge of this one molecule? 0. So I'm going to add electrons to which side? To the right side, how many? 2. Good. All right, so that's fine. Here I have 4 +1 ions. That's +4. Okay?
You're supposed to leave it 0.
No. They just have to equal each other.
Oh, okay.
Okay? All right, so this is +4. This is 1 ion, and it has a -1 charge. So this is -1. Okay? So what is the overall charge on this side?
3.
+3. Okay? All right. Does this have a charge?
No.
Nope, it's not. If it's not written, no charge. So this is a 0. Does this have a charge?
No.
Nope. Okay, so the overall charge is 0. Okay? So to which side do I add my electrons here? Left side, how many? 3. All right. Do my electrons lost and gained match? No. So what am I going to do to my top reaction? What am I going to do to my bottom reaction? Multiply by 2. Okay, so now I'm going to add them all up. I know some of you keep canceling out there, but it gets a little hard to look at. Okay? All right. So I'm going to have 3 times the 2 chlorides will give me 6 chlorides. And then I'm going to have 2 times the 3 electrons will give me 6 electrons. 2 times the 4 H pluses will give me 8 H pluses. And 2 times the permanganates will give me 2 MnO4s. So far, that's what's on the reactant side. That's going to yield 3 times the chlorine, and it doesn't matter what order you write these in at all, just as long as you have them on the correct side of the arrow. So 3 times the chlorine is going to give me 3 chlorines. 3 times the 2 electrons will be 6 electrons. 2 times the MnO2s is just that. And we have 2 times the 2 waters, so we have 4 waters. Okay. Is there anything that can cancel out? Electrons. And that, if your electrons don't cancel out, you got more work to do. Okay? Now, this is not, we're not done. Okay? But if it had been in acidic solution, we would be done. So now, this is where I add on to the steps. Okay? Does it make sense that we have H pluses if this is a basic solution? No. Okay? So what we're going to do is we're going to change this to a basic solution. So I'm going to add the basic ion. I'm going to add 8 OH negatives here. And what I do to one side, I have to do to the other. Okay? It does look like 80, but it's not. 8 OH minus. Is that better?
Yeah.
Maybe that's better. 8 OH minuses. Thanks. Okay, so now, what do H plus and H minus make? It makes water. Okay? Does everybody see that? It's like they're going to neutralize each other. So this really is making 8 waters. Okay? Now, is there anything that can be simplified?
Water.
Right. Okay, we have 4 waters here, and we have 8 waters here. So, I'm not going to keep scratching out because that gets hard to look at. Okay, so what we're going to have is we're going to have our 6 chlorides and our 8 waters and 4 waters. What's that going to even out to be?
4 waters.
These are going to go away, right? And this is going to turn into a 4, right? 4 waters. That's simplifying. I still have my 2 permanganates. That's going to be 3 chlorines. We already crossed out the electrons. Plus 2 MnO2s. Plus, we crossed out those waters, 8 hydroxides. And that is our final answer.
Oh my goodness.
Okay.
And I will tell you one thing. If you kind of notice, this works most of the time. Do you see how in our first answer we had H pluses over here, 8 of them, and we had 4 waters over there?
Yeah.
In the end, look what we ended up with. 8 OHs over there and 4 waters over here.
They kind of always switch.
They kind of always switch. I mean, yeah, okay? Now, here's the other thing. Remember we said, you know if you're right, if all the atoms balance, 6 chlorines, 8 hydrogens, 8 hydrogens, 4 plus 8, 12 oxygens, 4 plus 8, 12 oxygens. Your atoms have to balance, but your charge has to balance. Look at this. 6 times -1 is -6. This is 0. This is 2 times -1. So this whole side is a -8. Over here, 0, 0, 8 times -1, -8. It all balances. Okay? Whew. So Wom Doosley, Frank.
For the oxidation, why would we add 2 electrons to the right if the left charge is only negative?
This one,
Yeah,
there was 2 of them.
there were 2 of them?
2, we had that 2 in front before we did anything else. Because see the Cl2? We had to add a 2. Great, Dan, you do that. Thank you very much.